Hello, everyone. My name is Dr. Reza Said Kandezi, and today in this discussion, we are going to talk about the harmonic control in electrical power systems, and we are going to use the standard IEEE 519 as the framework. We are going to talk about how this standard defines how we could identify or measure or limit or mitigate the harmonic distortion in electrical system. And we are going to talk about some parameters that could quantify the harmonic distortion like THD and TDD. And also we are going to go over an example regarding this standard. Now, let's talk about the purpose and scope of IEEE 519 before we start the content of this standard. Now, this standard IEEE 519 basically provides some recommended practices and requirement for harmonic distortion control. So that means that this standard is a guideline. It is not a rule or mandation. Okay, so it tells the engineers how to reduce the unwanted electrical harmonics in the power system and improve the reliability and the safety in their system. Now, although it's not legally mandated, this is widely followed in real world. This is standard widely followed in real world engineering. So many utility companies, industries, and like engineering contracts require following this standard, so they make sure good power quality and avoid equipment problems. Now, this standard sets limits for how much harmonic distortion is acceptable at the point of common coupling, which we call it PCC, which is the place that facility connects to the power grid. And basically a standard IEEE 519 says how much distortion in current and voltage is allowed at this point, so we could avoid affecting other users that are connected in the same network. Now, this standard basically aims to protect the entire power system. It's not just for one individual device. So instead of focusing on fixing each piece of equipment, this standard ensures that the whole system, from the generator to the transformers to the end users, all of them work well together without harmonic issues. Now, it helps to make sure that the equipment from different sources can work together without causing any interference. So by keeping the harmonics under control, we can make sure that the sensitive machines don't fail or act in an unpredictable kind of like manner. Now, we have to note that this standard is designed, okay, and written specifically for the power system that operates at 60 hertz, which is the North American electrical network. So this is a very important piece of information, because that frequency, that fundamental frequency 60 hertz, affects quite significantly the parameters when we talk about the harmonic distortion and measuring the harmonics and limiting the harmonics. Now, this standard applies to the power generation. Also, it applies to the transmission and distribution networks. So basically the whole electrical grid. And it's not just for the factories or buildings. So basically it covers everything from the place that electricity is generated and produced to how it's transmitted over the long distances, and finally how it's delivered to the homes or like businesses. Now, there are some important concepts when we talk about the significance of the harmonics in modern electrical system. And for example, the harmonics today are more important basically because basically modern electrical system use many nonlinear loads. Okay, so unlike the old devices that basically used electricity in a smooth and predictable way, the new technology like computers or LED light or variable speed drivers pulls the current in a very sharp, irregular burst, which those basically behavior creates the harmonics in the signal. Now, there are some common sources of the harmonics that includes like devices such as the adjustable speed drivers or UPS, the uninterrupted power supplies, the switch mode power supplies, LED lighting systems, and like a welding equipment, and like these switch power supplies is a variety of the component that use switching devices inside them, like the inverters, for example, or like a StatCom, static compensators in the system. Now, these harmonics basically can cause extra heating in our system, which basically can damage the component over time. And the reason is if you remember the power loss equation, which is the RI squared, when we have a harmonic, that I in that equation contains several components. Each component has different frequency. Okay, so now basically the total power is a superposition of all those components. So we have RI squared at 60 hertz, plus we have RI squared at 120, for example, hertz, and again RI squared at 180 hertz, and so forth and so forth. So that basically means more power loss, which means temperature rise, and this basically reduces the equipment life expectancy. Now, those harmonics also can cause a malfunction or misoperation when we talk about the sensitive devices, like digital controllers or like a medical machine. And it's because they depend on a clean and a stable electrical signal, and any problem with the power quality, when the power quality is poor because of the harmonics, can make them respond incorrectly or even shut down during the operation. Now, those harmonics also can lead to insulation breakdown, okay, in a variety of the equipment. So it's not just one or two equipment or a specific equipment. So why that happens is because one reason is that temperature rise, that heat, that the extra heat that the harmonics cause in the equipment. So that would damage the insulation. But another factor is the extra stress, extra voltage or current stress that kind of like applied to those insulation. So they could get damaged. And if they damage, basically it could cause short circuit or failures. Now, another significant or effect of those harmonics, the problem that the harmonics cause, is that it reduces the overall efficiency, because this is like a physical fact that the conservation of the energy. Okay, so you generate a certain amount of energy, or you convert a certain type of energy to electrical circuit. The source has a specific amount of energy or power. Now, when you have harmonics, that the specific amount of energy would distribute between the component. Now, yes, the fundamental would get the most portion of that energy, but there are several other frequencies and other components that also took a certain portion of that fixed energy source. Okay, so you can imagine that because our system works with that fundamental frequency, with that 60 hertz, and it only wanted to like consume that, it designed to consume and work with that, all the energy that are stored in the other harmonics, they are basically useless for us. Okay, so they are basically energy losses. So that would reduce the efficiency of our system. And it's not just these problems. You know that every physical system has a natural frequency, which in that natural frequency, if you have like an input with that frequency to that, apply to that system would have a resonance effect and significantly boost that specific frequency input. Okay, so now imagine we have a power system that, like all the other physical system, it has a natural frequency. Now, if one of our harmonics, the frequency of the one of our harmonic matches that natural frequency, that means the system would boost significantly the size of that specific harmonic, which is could cause like an extra stress for the equipment, and also they basically could create a misfunction or misoperation in the equipment too. Now, those harmonics are also interfere with the communication system. Okay, especially the communication system that are shared over the power lines. Okay, so there are many control systems that basically modulate their data over the power signal. Okay, so the same wires that carry the power signal, they also carry the data, the measurement for the control system and monitoring system. So if we have a harmonics in our power signal, it could distort or even block those data signals. So it's cause failures in automation monitoring system. Now, we have, let's talk about the harmonics. Let's talk about what are harmonics. Okay, so define the harmonics itself. Harmonics are voltage or current components that happen at frequency that are integer multiples of the fundamental frequency. For example, when we talk about the 60 hertz power system, the fundamental frequency is 60 hertz. Now, all the multiples of that frequency, like the second harmonic it means like 2 multiplied by 60 is 120 hertz. The third harmonic is 180 hertz, and so on. So these are, which basically you can consider that like echoes of that fundamental frequency. These are considered harmonics. Okay, I need to correct my statement because I don't want it to cause any confusion. When I talk that you can consider, and I told you that consider it as echoes of this fundamental frequency in physical rigor definition, echoes has the same frequency. Now, this is like echoes, but at higher frequency. Okay, so they have same information, but in a higher frequency. Now, those harmonics happen basically when electrical waveform deviate from a pure sinusoidal shape. So instead of a perfect wave, the current or voltage becomes like bumpy or jagged because of some devices that use the power in an irregular pulse rather than evenly, like the old technologies that we had. Now, there are also some nonlinear loads, which are the main reason of the harmonics in the power system. So devices like computers or LED lights or speed drivers, variable speed drivers, they draw current basically unevenly. When I say unevenly, that means there is no symmetry in their signal. So the positive half signal could be different from the negative half signal, and even like the one cycle could be different from the another cycle. This is kind of like, but most importantly, the positive and negative signal are not don't have the symmetry that we have in the pure sinusoidal wave. Okay, so it also introduced the harmonics in the system. Now, a pure sinusoidal waveform is smooth and continuous, but a distorted waveform contains like an unwanted ripples or notches in the system. Now, when we want to visualize the harmonics, we can use the frequency spectrum, which shows some spikes that include the amplitude of the fundamental frequency and all the harmonics and their frequency. Okay, so like in the frequency domain, the perfect wave, a pure sinusoidal, only shows, when we talk about the frequency spectrum and pure signal, it only shows one spike and it's at the fundamental frequency. But when we have a distorted signal, if you remember the Fourier series and the Fourier transforms, we have several different frequency, which in the spectrum shows by showing several spikes at each harmonic frequency. Now, as we said and mentioned the Fourier series, the harmonics that we talk about mathematically can be analyzed basically using the Fourier analysis. So Fourier analysis basically breaks down any complex arbitrary waveform into summation of some sinusoidal, pure sinusoidal waves with a different frequency. Okay, so like for example, we have arbitrary waveform, and we could use the Fourier transform and Fourier series to represent that arbitrary waveform as a summation of like a sine and cosine wave at the fundamental frequency and the second harmonic and the third harmonic and the fifth harmonic and so on. So this is basically the mathematical representation, the way we could represent mathematically those harmonics and analyze them in our system. Now, we can classify the harmonics from different aspects. Okay, one aspect was that we talked about is based on the harmonic order. So we have different orders of the harmonic, which refers to how many times their frequency is compared to the system base frequency. So like that 120 hertz is the second order harmonic. Okay, so like that. So for example, in 60 hertz, the third harmonic is 180 hertz. Okay, and like lower order harmonics, like the third order, fifth order, and seventh order, are the most common harmonics in the system. They have the highest amplitude normally in our harmonic spectrum and the frequency spectrum, and we need to pay more attention to those low order harmonics. Now we have also higher order harmonics, like 17 or like 19 or even higher, which usually created by fast switching, like in the inverters. Like the switching frequency of the inverter is also considered as high frequency, because like, for example, if we have a frequency, the switching frequency equal to 1200 hertz, okay, so in a 60 hertz frequency, that's the 20th harmonic. Okay, so this is the higher order harmonics. And normally it's in a switching that use the PWM kind of switching in their control system. And what is wanted to like mention also, when I mention when we talk about those kind of devices, I have to add another aspect about the significance of the high order harmonic and low order harmonic. We said that low order harmonics are the most important one because they have the most higher and the highest amplitude in the spectrum. But when we have a switching devices like inverters that have like a PWM and has a higher frequency of the switches, that specific frequency would also peak higher than the rest of the spectrum. So when we talk about the inverters, for example, the low order harmonics are important, but we also have to take care of the switching frequency. Now, The harmonics also can be classified and grouped by their phase rotation. In the three-phase system, we have three types of the sequence: positive sequence, negative sequence, and zero sequence. Okay, positive sequence is when the three-phase rotate basically in the order of A, C, B. This is positive sequence. Now, if it rotates in order of A, B, C, it is negative sequence. If it doesn't rotate at all, okay, it's zero sequence. Now, you might say, okay, if we have a frequency, how come it would not rotate at all? Now, you can imagine the triangular kind of like characteristics of the sinusoidal frequency. So when we have three phase, okay, if we add them together, the summation of the three phase, the summation of the three sine that are 120 degree, that have 120 degree phase difference, they are going to be add up to zero. Okay, so now in the third harmonic, sixth harmonics, nine harmonics, and all the multiples of three, okay, all the orders that are multiples of three, okay, all of them would scale that 120 phase degree with the same order. So eventually the summation would be zero, so we don't have any rotation. Now, the harmonics also can be divided based on their source. It could be characteristic harmonics that are generated by a predictable source, like rectifiers, or non-characteristic harmonics, which are normally caused by imbalance or poorly grounded or like a resonance situation in our system. Now, we mentioned that we have two parameters that quantifies the harmonic distortion in our system. One is THD, which is short for total harmonic distortion, and the other one is TDD, which is short for total demand distortion. Now let's talk about them. Let's define them. What are those parameters that can help us quantify the distortion caused by harmonics? Now, THD basically tell us how much of a waveform is made up of the harmonic frequency instead of the main signal. So what's going to happen is the THD measures basically percentage of the distortion in a current or voltage by comparing the strength of those harmonics to the strength of the fundamental frequency. You can see the equation here, like for example, for THD in the current, the denominator contains the summation of the squares of all the harmonic components, which is the strength of all those components. Then we run under the squared sign, okay, and the denominator is the fundamental frequency. Okay, and remember those values are RMS values for each of the harmonics. Now, this like example, current THD shows how much of the current waveform is distorted. Okay, the voltage THD works on a distortion in the voltage waveform. Now, THD is an instantaneous measurement, so it can change depending of how much load is being used at the moment. So the measure that THD might look high when your system is lightly loaded, not because of the real problem, but because of the fundamental current is small. But it could change when we change the load, which means the current, the fundamental current is changing. Now, the other quantification is total demand distortion, TDD, which is more stable measurement and compares the harmonic current to the system's maximum load current. So we don't have real-time current like the THD. We only consider in the denominator the maximum load current. Now, TDD is the main metric that is used in the IEEE 519, so we could check the compliances with the harmonic limits. Okay, so basically by using the TDD instead of a THD, we can get a clear picture of a long-term harmonic performance in our system and the impacts of that in our system. Now, let's talk about the harmonic distortion and spectral analysis. Now, time domain analysis basically shows how the voltage or current changes over time. So the distortion appears as like a wave shape irregularities, like flattening or notches or spikes. Okay, this means when you look at the signal on the, like for example, oscilloscope or a graph, in a clean waveform, a clean sinusoidal, it looks smooth. Okay, but when we have harmonic distortion, it makes the signal to look jagged or uneven or chopped in a certain places. Now, frequency domain analysis basically transform that time-based waveform into a frequency components. We normally use fast Fourier transform as a tool to do that. So instead of seeing how the signal changed over the time, we use that fast Fourier transform to develop the Fourier series of that arbitrary distorted signal. And we can see how strong each frequency is, so we could help identify which harmonics are present and how large they are. Now, harmonic spectrum plots normally display the magnitude of each harmonic order. So it gives us a visual fingerprint of the distortion in our system. Like, for example, if the fifth and seventh harmonic are dominant, we see large spikes as those frequency in the plot. Okay, so which basically tells us exactly where to focus when we want to like mitigate the distortion. Now, analyzing the harmonic spectrum helps help us to determine whether the system actually comply with the IEEE 519 or we need to correct the system. So that analysis, the frequency analysis, is very important for tracking down the source of distortion and basically choose the right solution to reduce or mitigate that harmonic distortions. Now, we mentioned that we measure the harmonic distortion at point of common coupling, or what we call it PCC. Now, that point of common coupling, the PCC, is a key location in a power system. Okay, so we assess or measure the harmonic distortion at that point. And as we said, is the point that facilities in electrical system connect to the utility grid or other customers. You can see the schematic of example for the power system. Now, PCC is important because harmonic distortion at that point can affect not just our system, but other users that share the same network can be affected. Okay, so that the PCC basically makes sure a fairness by providing a consistent and a standard place to evaluate the harmonic impact. Now, the common PCC location include the low voltage side of the utility owned transformers after the main service disconnect or at the switchgear where multiple feeders are combined. So this means it's usually found right after the point where the utility hands over power to the customer. So or like at a central node where the different parts of a system connect to each other. Now, it basically helps to separate the local devices level issues from system level distortion. Now, the IEEE 519 sets some limitation for the harmonic distortion. And it's different. The harmonic limitation for current and voltage are different. Now, we have several requirements when we talk about the compliances with the IEEE 519. One component, one criteria is the ratio of the short circuit current to the maximum load current. Another one is that standards actually define some threshold, some criteria for each individual harmonics up to the 11th harmonic. Okay, and we also define a TDD, which actually contains all the other harmonics as well, and it is a percentage of the distortion over the maximum current, the load current that we have. Now, this standard basically sets these limits on how much harmonic current the facility is allowed to inject into the system. Okay, so when you want to, like, for example, connect your factory or your manufacturing line to the system, okay, you have to make sure that you are meeting the limitation mentioned in the IEEE 519. Okay, so it's very important because it would distort the system. And normally, like in the industrial scale, if you exceed these limits, normally the utility would charge you with a certain amount of penalty in your bill. Okay, so this is kind of like, because it's creates problem with the power quality of the system and the stability of the system. Now, this basically allowable harmonic current depends on the size of your facility. Okay, so it's compared to the strength of the electrical system at the point of common coupling. So this is measured by the ratio of short circuit current over the maximum load current. A smaller ratio means your system is weak compared to the grid. So the stricter harmonic limits will apply. And the higher ratio means your load is small compared to the grid strength. So you're allowed to inject more harmonics without any type of creating any problem for the grid. Now, as we said, this standard defines a certain criteria for those ratios. So it categorize those ratios. Okay, for example, if your short circuit current over the maximum load current is less than 20, okay, that means your TDD are limited to the 5%. But if, for example, your ratio, the ratio of the short circuit current over the maximum load current is over 1000, now you're allowed to inject 20% total harmonic distortion, or total demand distortion is limited by 20%. You can see how changing the ratio could change the criteria for your system. Now, the table, as we said, and you can see, also sets individual limits for a specific harmonic order, like fifth or seventh. Okay, especially the lower the harmonics. So it ensures no signal harmonics become too dominant. So these limits apply at the PCC, not individual equipment. So it's a system level performance. Okay, so you have to make sure that this approach avoids unnecessary over design and encourage a smarter system-wide planning and filtering. Now, beside the current, we also have some limitation for voltage, harmonic voltage distortion, which basically the standard sets limits on how much voltage distortion caused by the harmonic is allowed in the power system, so it could protect the equipment and make sure that we have a reliable operation. Now, these voltage distortion limits depend on the system's nominal voltage level, which means the voltage rating of the power system affects how strict the limits are. So higher voltage systems generally have tighter limits because equipment connected to them is more sensitive and failures can be more severe. For system below like 69 kilovolt, the IEEE 519 allows a maximum total voltage harmonics distortion, the THD, of 5%. And for system, the maximum, I'm sorry, for above the 69 kilovolt is 3%. For below the 69 is 5%. Now, for medium voltage, like between the 69 to 161 kilo system, this standard defines 1.5%. And when we talk about over 161 kilovolt, we have a limit of 1% for harmonic distortion in our voltage. Now, we mentioned earlier that the harmonic components are the integer multiples of our fundamental frequency. But this is not just all the components. These are the main components in the harmonic spectrum. We have some other special harmonics. We call it inner harmonics and subharmonics that also exist in our system. Now, inner harmonics are non-integer multiples of the frequencies, so they exist between the integer components. So, like for example, 100 hertz in a 60 hertz system is an inner harmonic because it sits between the first fundamental component and the second harmonic. Or like 200 hertz sits between third and fourth harmonic. Now, we also have subharmonics, which are the frequencies that are below 60 hertz. Okay, we call those subharmonic component. Now, inner harmonic are normally caused by power electronic that use PWM pulse width modulation or variable switching frequencies. Okay, but and they can cause problems like flickering the lights or control system instability and interference with power line communication. Now, subharmonics, as we said, are the harmonics that are below the fundamental. They normally happen in the inverter-based system during the fault condition or a resonance situation. And it normally leads to unusual oscillation or instability in power system that are very difficult to detect and mitigate because all our measurements are based on 60 hertz, okay, in the system. So subharmonics are harder to detect and mitigate. Now, that standard IEEE 519 mainly focuses on the harmonics up to 15th order. Okay, but inner harmonics and subharmonics are also like kind of like emerging concern because of the rise of the advanced power electronic equipment. So in like modern devices, as they become more complex, monitoring and controlling of these special frequencies becomes very important for maintaining the power quality. Now, one of the type of the distortion that could create the harmonics, the most two common one actually, are voltage notch and the transient harmonic. Beside the switching, okay, so we know the switching happens. So if you have a PWM, it's basically the voltage and the currents are the train of pulses. Okay, so they introduce harmonic component, but beside the switching devices, the system nonlinear behavior also can create harmonics. The most common one is the voltage notch and the transient harmonics. Now, the voltage notch is the sudden short dips or like irregularities in the voltage waveform that happens in a system with the devices like SCR. Okay, so that voltage notch can cause equipment to malfunction or premature aging. So this IEEE 519 specifies some assessment criteria for voltage notch, including the notch depth and the total area under the notch. You can see in the slide in the graph what we meant by notch depth and notch area. These criteria make sure that the voltage disturbance stay within an acceptable levels and typically not exceeding 1% of the peak voltage. Now, here we consider the peak voltage as a reference. Before in THD and TDD, we use the RMS value, so be careful about that. Now, transient distortion basically refers to a short duration, very sudden changes in the voltage normally. It's normally caused by capacitor switching or like a motor starting or system faults. Okay, so it's very fast and can excite the resonance in the system. And also, as you can imagine, it introduce harmonics into our system. Now, that transient harmonics are typically measured using a high-speed digital fault recorders. Okay, that those transient events are captured. They use those oscillography or high-speed digital fault recorder to capture the fast and complex nature of those transient. Now, again, we know that IEEE 519 mostly work with the harmonics, kind of like focus on harmonics, which are a steady state factors Why steady state factors? Because for evaluating harmonic or measuring the harmonics, we need at least one, theoretically, at least one fundamental frequency cycle. Okay, so we could run the Fourier series. But in a real world, the equipment that want to measure the harmonics, they need like 3 to 5 cycles so they could settle the THD and TDD to the stable limits, okay, and measure that. Now, that IEEE 519 mainly addresses the steady state harmonics. So the transient event basically can trigger resonance that actually makes the harmonic distortion worse over time. So this means that the controlling the transient is important, so we can have we can prevent the long-term power quality issues. Okay, so managing basically the voltage notch and the transient distortion, they require careful design and coordination of the switching equipment and the protective devices. Now, we said that we have some primary source of harmonics. One would be the industrial power electronics like variable frequency drives or DC drives and tristor controllers, which are the major source of the harmonics. Commercial and residential loads like switch mode power supplies, LED lighting, and like electronic blast also contribute to this harmonic distortion. Now, distributed generation system like solar inverters or like wind turbines and battery storages add some complexity by producing harmonics and also inner harmonics to the system. And beside that, nonlinear loads are also one of the primary contributors to the harmonic distortion because they draw current unevenly and their current, the current that they drain, doesn't follow a pure sinusoidal wave. So they don't have a symmetry, they have like a distortion on that sinusoidal wave. Now, different sources produce different harmonic orders. For example, like VFDs normally creates like a strong 5th, 7th, and 11th and 13th harmonics. Commercial equipment like SMPS that we mentioned often generates a strong like 3rd and 5th harmonic current. And but the renewable energy system add new challenges because they introduce inner harmonic and some higher frequency harmonics. We said there's a switching aspect in those, so we have like a switching frequency that are normally in the range of the kilohertz. We would have a strong higher order frequency too. And as we mentioned, there is an inner harmonic introduced by those devices, which traditional filters may not handle those very well. Now, harmonics, okay, can impact different type of electrical component differently. For example, they can cause increase of eddy current and core loss in transformers. So basically, it leads to the overheating of the transformers. When we talk about the capacitor banks, they can experience the harmonic resonance with the system inductor. So they would experience some overvoltages or even failures because of the harmonics. Electric motors basically suffer from the harmonics because those harmonics, which are not the same frequency that the motor should work with, create some like torque pulsations and vibrations, which basically reduces the efficiency and the lifespan of that motors. Now, in cables and conductors, as we mentioned about the power loss, they can suffer from the heat caused by that RI squared power loss that we talked about, which basically creates a lot of damages in insulation, especially in the neutral wire, when certain harmonics basically add up to each other when we talk about the three-phase system. Now, we also have one of the sensitive one is the protection system, like relays and switchgears, that they can experience kind of like incorrect operation and tripping because of the harmonics. So that distorted current and voltage can basically confuse the protection system. So it made them to have like false trips or failing to detect a real fault. So overall, the harmonics distortion stresses the equipments in electrical system. It reduces the efficiency and also increases the maintenance costs and the risk of unexpected failure. Now, there are some system-wide impact that harmonics can cause. Like, for example, the harmonic currents following through the power system impedance distort the voltage waveform, affecting both downstream and upstream users. So this means when we have a distorted current that travels through the network, they basically cause voltage to become irregular. You can imagine this is Ohm law, okay? So not only at the source, but also at all the points connected to that system, we would face that problem. Now, in a weak electrical networks, those voltage distortion from the harmonics are more severe because the system cannot absorb the distortion effectively. The weak network, the weak grid situation, we have lower inertia in our system. So if there is any disturbance, system cannot handle that distortion because it has not enough inertia to deal with that. So weak networks have like a low short circuit capacity. Okay, so even a small harmonic currents cause like large voltage disturbance, which impacts some sensitive equipments. Now, we have resonance condition that we mentioned that can amplify some specific harmonics. So they make their effect worse, much worse actually, in certain parts of the system. We could have a series resonance, okay, that is caused by high circulating current in a localized part of our network, damaging the equipment and causing overheat. This happens when inductive and capacitive elements basically line up in series, leading to a dangerous current spikes in that specific area. We could have parallel resonance that can increase the voltage distortion across the system, which stresses the insulation and sensitive device. Now, here, the inductive and capacitive component in the system resonate in parallel. So they magnify the voltage harmonic. Okay, so now, harmonics can also cause grid forming and grid following inverters that are distributed energy resources to lose synchronization with the grid. So this loss of synchronization also can make renewable energy resources unstable. So it reduces their ability to support the grid, and it leads to a disconnection of those equipment. So this excessive harmonic may also violate grid codes and the interconnection standards. So basically, we can face penalties or forced equipment modification or disconnection from the utility. Now, there are several approaches that we could take to mitigate the harmonics. They can be divided into load level and system level solutions. Now, load level solutions normally involve like installing a filter or a device directly at the harmonic producing equipment. Okay, that means treating the source of the harmonics. Okay, the system level solutions includes methods like using harmonic mitigating transformers or phase shifting transformers and coordinated filters throughout the network. Now, we have passive filters that use fixed reactive components, okay, like inductor and capacitor, and they have resistor to control the level of the current and the natural frequency of the system. So they are tuned to block or absorb some specific harmonic frequencies. They are simple, they are reliable and cost effective, but work best for known steady harmonic frequencies. Okay, so now, on the other hand, we have active filters that normally use power electronics and digital signal processing, so they can detect and cancel harmonic dynamically in real time. These filters mostly adapt to changing harmonics conditions and can handle a wider range of the frequencies, but they are more complex and much more expensive. Now, we can have hybrid filters, that is the combination of the passive and active filters, so we can balance the cost and the performance. And the choice of the mitigation approach basically depends on like harmonic source characteristics, cost, system complexity, and requirement that we have for the performance. Now let's go a little bit deeper to the passive filter techniques. Now, passive filters are, as we said, made from simple electrical component, or LC, resistor, inductive, and capacitor. And they designed to block some specific harmonic frequency. So those filters don't need power electronics and work by creating paths that divert or reduce the harmonics at targeted frequencies. Now, we could have single tune filters, which we call it notch filters. They are designed to target one specific harmonic order, like fifth or seventh, by using a series LC circuit connected in parallel with the load. Okay, so basically they offer a very low impedance at the tuned frequency, allowing the harmonic current to flow through the filter instead of the main system. This is based on the current division rule that we have in the electrical engineering. Now, we have high pass filter, okay, which are designed to mitigate high frequency harmonics, normally above the 25th harmonic, and provide a low impedance for those harmonics. We have C-type filters that combines a series and parallel LC components, so they could reduce the losses at the fundamental frequency and provide some like efficient continuous harmonic filtering. We could have multi-stage filters that combine several single-tuned and high-frequency filters to handle a wider range of the harmonic frequency when we talk about a large industrial system. Now, as we said, passive filters are cost-effective, they are reliable, and require little maintenance, but they have a limited flexibility since they are tuned to a fixed frequency. Now, we said that we have also active harmonic filters, which use power electronic and digital controllers to dynamically detect and cancel the harmonic currents in real time. Now, these filters basically sense the distorted current waveform, extract the harmonic components using that FFT system, fast Fourier transfer, and inject the same frequency, the same harmonics, but with the opposite kind of like with the opposite current back to the system. Like what I mean is that, for example, let's say we have second harmonics with a certain amplitude. Now, what it does, it creates the same frequency with the same amplitude, but with 180-degree phase shift. So now the positive half cycle of the main harmonics is going to be canceled out by the negative half cycle of the injected harmonic by the filters, and also like the negative half of the main harmonics is going to be cancelled by the positive half of the active filter injected signal. They normally are connected. These active filters are connected in parallel or shunt in our system. There are some series or hybrid combination, but most popular one is shunt active power filters. These filters can also compensate unbalanced load and reactive power support, and provide the reactive power support for the system. So they are not just eliminating the harmonics, they are very good for the power quality of our system. But as we said, the active power are complex and expensive, but while they are complex and more expensive than a passive filter, they basically offer a better performance in the system, okay, when we have like an unpredictable and dynamic harmonic behavior. Now, let's now that we discussed the situation, let's go over a certain example to see how the IEEE 519 compliance is assessed. So we can like walk through a complete network example that illustrate the full process from identifying the non-compliance factors and up to the solving those problems, so we could make sure that our system is aligned with the IEEE 519 standard. What happened? Sorry. Okay. Let's assume that basically we are evaluating a compliances of an industrial facility that is connected in a 480 volt. It is three-phase industrial facility. The maximum demand load current, that IL that we mentioned for the TDD, is 300 amp. And we know that our short circuit current is 9 kiloamp. So based on these two factors, we can calculate our short circuit to the demand load ratio for the current, which if we divide the 9K to the 300 amp, we get the 30, which falls in the range of the 20 to 50. If you remember the table, we have several range of the ratio that would define the limitation for the TDD and the harmonics. So it falls into that interval in the range. Now, we run a measurement at the PCC here, okay, and run a fast Fourier transform, and we find out that our 5th, 7th, and 11th harmonics, the rest of our are consider the rest as 0. But these 3 components are 22 amp, 18 amp, and 12 amp. Okay, which all of them exceeds the limit that defined by the IEEE 519. Now, for that specific ratio, the 30 that we calculated, the TDD limits in the standards is 8%. But when we calculate the TDD for these harmonics, how we calculate it? It is this formula, this equation. TDD is equal to square root of that 5th harmonics, 22 square plus 18 square plus the 7th harmonic and the 11th harmonic 12 square. We add these, make a square root, divided by the load demand current, that 300. And if you calculate that, it is 10.29%. There is a multiply by 100, so we could make it percent. Okay. Now, as we see in our calculated situation, we can see that the standard do not follow the limits of limit described by the IEEE 519. So the individual harmonic should not exceed the 21 amp. These two are okay, but the 5th harmonic exceeds the limits. The TDD should not exceed the 8%, but we see that in our situation, we also do not meet this criteria. So now we have problem, and we have to fix that problem. How we could do that? We have 2 options. Either we can use a passive filter to compensate or to mitigate that excessive harmony and reduce the TDD to the limit. Another option is active harmonic filter. Now, let's begin with the passive one. So we start with a single tone filter. So we will assume that the system, as we said, works in 480 volt. So the nominal voltage is 480 volt. Line to line, this is the line to line, which basically means that the voltage of the line to neutral is 227 volt. And we want to target 50 kilowatt capacity for our filter. So at the fundamental frequency, at the 60 hertz. Now we can calculate the capacity reactance required at the 60 hertz. So if how we could calculate, let me write down the formula so we make sure that we know everything. So to calculate the capacitive reactance XC, we know that the capacitive reactance is V squared over the Q. Now, this Q is the kilowatt that we described, and that V2 is that line to neutral voltage. So if we do that, it's going to be 277. 277 square over 550K. Okay, which means 1.530. Okay, so now we have 1.53 ohm, and we know that the C, the capacitance of that reactance, is calculated by 1 over 2 pi f x c. You put all the values, so this is the x, f is 60 hertz, so the C become 1 point, if you calculate that, 1.74 millifarad. Now that we have the C, now we have to tune the circuit to the fifth harmonics because we wanted to target that. Now, how we could do that? We have to cancel out that fifth harmonic. If we want to do that, the L that we need for this filter, so it would work with the C and cancel out the fifth harmonic, is going to be calculated by 1 over 2 pi f squared. I'm not going to talk about the formula. You can find those formula in the textbooks. I'm just using it as an example. 2 pi f squared is over that. F all square multiplied by C. This F is for the fifth harmonic, so it's 300 hertz. We have the C here. Okay, so that L become 1.61 milli. Now we have our capacitance and our L. Okay. Similarly, we could use to address also the 7 harmonic and 11 harmonic if we wanted to address those. Now, if we do that and add that filter, after the mitigation, when we see the measurement, we could find that, okay, our post-mitigation TTD fall from the at 10.29% to 5.03%. So now we are under the limit. The limit was 8%. The fifth harmonic reduced to 12 ampere. We are below the limits. And because of that filter, it also affected the seventh harmonic, okay, which reduced the seventh harmonic from 18 to 8. Okay, so this is how we kind of used that passive filtering to mitigate or solve this problem that we have now. Our system is in the compliance with the IEEE 590. Now, let's talk about the active filter too. Now, let's consider a more advanced one. Okay, so we wanted to do the active filter. In the measurement stage, the CT is the current transformers, which installed in the installed in the system, measures the current, and then digital signal processors continuously samples the current waveform so they can extract the harmonic components using that FFT. Now, those controllers isolate the harmonic spectrum and generates an inverse harmonic current, okay? So they could effectively mirror the distortion. Now, a voltage source inverter inside the active filter, normally using the IGBT modules, injects a compensation current in real time, okay, which is properly tuned so they could ensure that the high frequency switching noise is also filtered. We could have series active harmonic filters or shunt filters. We choose shunt for current distortion. So it's installed in parallel with the load at that PCC. Now the load changes dynamically. So if that changed, that filter would basically adjust the injection based on the dynamic of the load. And this is basically, these examples demonstrate how IEEE 519 compliance is assessed based on the real-time harmonic data and a kind of like a quantitative threshold that are tied to the system size and the load. Now, for the active harmonic, we didn't mention the numbers because it's mostly the design, it's mostly the control system. We have like the IGBT-based inverters, which is an H bridge, you know the H bridge. And there is a control system using the PWM that tunes the control system and the output of that active filter in a way that they could inject the same harmonics, that fifth harmonics and 7 harmonics and 11 harmonics. If you remember, we have 12 amp of 11th harmonic. They could inject those signals by 180-degree phase shift, so they could cancel out these harmonics. And this is mostly the control system works. This is the signal processing control system works. So normally you can use a PID control system to manage this goal. Now, understanding basically this workflow is very important for us to maintain the grid integrity and reduce the power quality penalties and meet the interconnection standards. Okay, so this is very important when we talk about the power quality. This is our discussion for today. Please let me know if you have a question. Otherwise, thank you for your attention.